This is Viterbi Voices, the podcast, your chance to hear stories about research, classes, student life, and more directly from our faculty, students, and other members of the engineering community here at the University of Southern California.
This is episode 105, featuring Dr. Michelle Povinelli from the Electrical Engineering Department. Tune in for a really cool episode about her academic background, her interest in nanophotonics, and her incredible research on the many possibilities and capabilities of concentrated laser beams.
Welcome back into Viterbi Voices. This is episode
105.
105. Are you into numerology?
No.
Do you know what it is?
No. What is numerology?
I don't know either, but here's what I do know, and maybe people can email us to correct this if they're really into it. But supposedly, when you add numbers together, it gives you like a single-digit number, like 1 through 9. Mm-hmm. And then there's certain vibes that come along with it. And I don't know, I probably should have thought of this before we started recording, but when we said 105, I thought, oh, that equals 6.
Yeah. I think that, wouldn't that change from like culture to culture too? Because everyone has like different lucky numbers and different like auspicious numbers. I
don't know.
I'm curious. Now I'll have to look it up.
Now we have to look up lots of different things,
Stay tuned for 106, because I feel like 7 is a lucky number.
Right, so like there's...
So, 106.
Well, like I remember when my daughter was born, like if you put together your date of birth, you can come up with a single number, and then you can put together other single numbers to kind of figure out what it means and what your number is. And so this would be, like you can put in your birth date, right? Yeah. So what's your date of birth?
September 9th.
You can cut out your actual, you can cut out the actual stuff here, because I'm going to ask for your actual year too.
That's fine. People can know I'm born in 1997. I'm 21 years
God,
old.
you were born in 1997?
Yeah.
I hate asking people their ages. It makes me feel so old.
You were in college by 1997,
I was
right?
in college.
Yeah.
I was in college. So you're an 8, right? So you're an 8, and you're a sun sign.
Interesting.
No, that's your...
I know I'm a Virgo. I got to LA and people started talking about horoscopes, so now I'm like, I know I'm a Virgo.
This doesn't tell me anything what it is, but basically you can have a whole numeroscope, like a horoscope based on your number, right? Not just like what it all adds up to be.
Yeah.
I have no idea what it means, but this is a 6.
Stay tuned for updates.
I don't know why I brought this up. This is ridiculous. On this episode, Rhea, we have Dr. Michelle Povinelli from our Electrical Engineering Department.
Yes.
You had never met her before.
I had never met her before. She is an EE professor. So the course that she teaches for freshmen is a physics course.
Which is super cool.
Which is super interesting. She talks a little bit about that at the end. But her research is in nanophotonics, which is really interesting.
We're talking a lot about lasers. We're talking about heat. We're talking about radiation, which I guess is the same thing now. I just realized I said the same thing. We're talking about optical tweezers, which is the recent Nobel Peace Prize, and some of the work she did. And she very kind of undercut herself a little bit, but basically the work she did had contributed to it, and that work had contributed back.
Yeah.
Photovoltaics and solar power. We talked about basically using light to move things, using light to manipulate things. This was a really in-depth technical conversation, unlike our numerology conversation we just had.
No technical anything whatsoever.
Maybe it's because it was such a technical conversation I had to lighten it up with numerology ahead of time.
Yeah.
But she is a fascinating and brilliant professor here, of which you, as an undergrad, if you come in, you'll more likely have her. And if you're interested, she also gives a pitch at the end about just the importance of getting involved in research as an undergraduate and how that's an important part of our landscape here. But I don't want to spend too much time on this, because because we already spent way too much on numerology, which we also didn't tackle. But let's hand it on over to Dr. Povinelli to talk about her work in nanophotonics and everything else that she does.
Cool.
Hello, how are you? Good to see you. We're going to have you a sip.
A little cold and wet.
Just a little.
Yeah.
It was really light when I was coming in, and then when I was walking across campus, it just started pouring on me.
Yeah.
And I was like, of course, it's like while I'm walking.
Yeah.
And I'm never prepared for rain.
January, I was talking to people about this morning. I was like, January is always wet in LA, but I always forget about it every year. Yeah.
Yeah. The only reason I ever remember is like some of our events happen in February,
yeah.
and it's always like raining in those. Well,
To tell people this isn't the normal. Really? 90% of the year will be beautiful.
That's the best part about whenever it rains and we have visitors on campus. We always start with like apologies. I don't think we really even mean to, but it's like, I'm sorry, it happens to be raining right now. It never is. It just happens to be right now. So, thank you for coming. Appreciate it. That is yours. So you get the official mug. Really cool. So use it and support it. Thanks for coming on. Are you a big podcast listener?
No.
No? Okay. Well, hopefully this will make you one. At least just to listen to yours. I don't know if you had a chance to check out the other episodes.
I haven't, but I got the idea.
Okay, cool.
From your email.
Good. Yeah, it's basically just
Did not do
chat.
the homework.
No. There's no homework needed.
I got
The less you think about it, the better. It's always sometimes we get some faculty members before they come in. They're like, "What questions are you going to ask?" I'm like, "I don't know. We're just going to chat."
Very free form, very loose.
Where are you from originally?
Ohio.
Ohio. What part of Ohio?
Cleveland, Ohio.
Cleveland. Now, did you stay there all through high school? Or
yes.
Okay. Wow. Okay. And my family is from Ohio, actually. My mom's family is from Wapakoneta, Ohio.
I don't know where that is. Where's that?
South. Of course, now I need to know the geography of Ohio, which of course I don't know.
South of Cleveland.
I'm going to say southwest, but I'm not exactly certain. It's near Dayton.
Oh, okay. Yeah.
If that's any of help.
Southwest.
That's southwest? Okay, good. I got it right.
There you go.
And so you grew up in Ohio, and where'd you go to undergrad?
University of Chicago.
University of Chicago. Wow. How'd you like it?
Good. It's a very intense place.
I bet.
I've heard, yeah.
Dr. Armani went to University of Chicago as well, right?
We did not know each other because I'm 4 years older.
Okay.
About something like that.
Just missed each other?
We didn't overlap, yeah.
Okay. Because she studied physics there,
Me
if
too.
I'm correct. So you actually went through the same program as Dr. Armani. That's crazy. Wow. And just 4 years behind each other.
Yeah.
Wow.
We might have even worked in the same undergrad lab. I'm not sure.
Are you
It's
really?
possible.
Really? Wow. That's
Small
crazy.
world.
Can't verify that at the moment. But
Well, now we're going to have to do some
might have
research.
interned for the same person. Yeah.
Oh, my goodness. Did you meet each other here?
Yeah.
Okay, wow. And so you did your undergrad in physics at University of Chicago, and then you went on to graduate work where?
Well, I first went to University of Cambridge on a Churchill Fellowship.
Wow.
And I got a degree which doesn't exist in the U.S. So there is a one-year degree called an MPhil.
Okay.
Where you do a research project with a professor. And so that's what I got there. And then I went to grad school for a PhD.
Wow.
Yeah.
Oh, very cool. And you PhD at Cambridge?
No, so PhD at MIT.
At MIT. Okay. And how did you enjoy MIT in the Boston area?
Boston is amazing. It's a really great place to be a grad student. It's a good place to be any kind of student, I think. There's tons of students around. There's a good subway system. You can get around without a car.
Yeah.
The tea?
The tea is really nice.
Yeah.
Yeah.
Yeah, it's
really good.
Universities overlapping on top of universities there.
Yeah.
I always wonder what people do in Boston outside of that, because there's just a lot of universities.
I think there's some number, like there's 50 or so, some kind of university in Boston.
There's 50?
Like between like trade schools and then universities.
Really?
And like art schools and stuff like that. There's just like 50 of them.
Wow.
Yeah, it's crazy. It's like a big college city.
Do you ever get back to Boston at all?
Every couple years.
Every couple of years? Okay.
For conferences or something at MIT.
Just some get-togethers?
Yeah, well, for example, so usually when professors get close to retirement, or maybe not even close to retirement, maybe just a bit older, all the former students will get together and have a birthday celebration for the professor.
Yeah.
But because it's for a professor, it's not a normal birthday celebration. The former students come and give research talks. So you have a
for a birthday
symposium.
talk?
Yeah, so this will usually be, people will either do it for 65th or 75th or sometimes both. And then students come and give talks. So I went to one of those for my PhD advisor a couple years ago. So that might have been the last time I was in Boston. So
that's cool.
I was at MIT for that.
That's cool.
That's really cool. It's a very informative birthday.
Very informative birthday.
Learned a lot.
Well,
They're usually a combination of, the talk will be part research, part jokes.
Balances out.
When I was in grad school, I had mice under my desk.
Okay.
This is at MIT, and so part of my talk...
I was going to say, as part of your experiments, or is this they were just living in the building?
There were just mice. So we were in an old building, and my office was across from a door which was permanently closed and led to another area that you couldn't get into through that door, only through a different door.
One of those like university reconstructions where they're like, there's a door there, but it's going to cost so much money to make it a wall, so we're just going to lock it off.
Yeah. So these mice would, the mouse would pop its head out from under the door and kind of look around. And then sometimes the mouse would go retreat again, and sometimes it would run across the hall and under my computer. And,
Did you have a name for the mouse?
No one else seemed concerned.
Did you have a name?
No.
No. I've heard.
Periodically I would go and be very upset and try to tell someone that there were mice and that this was a problem. And they'd be like, oh yeah, mice.
It's one of those things for some reason that like old university buildings, like in some of our older buildings on campus, you hear these stories of like, you know, these little critters that might be rumbling around. Or whenever there's construction on campus, whenever they dig up something, there's always something comes out. Like there's always like all of a sudden like, oh no, we've got these mice over here or something else happened. So you're at MIT, and then what happened after MIT? What happened between that and taking your position here?
I did a postdoc at Stanford in electrical engineering with a professor who had been my group mate at MIT.
Cool.
So when I started as a grad student, he was just leaving for his faculty position at Stanford. And then when I graduated, I went and did a postdoc with him.
That's great. Is your PhD in electrical engineering from MIT?
Physics.
In physics.
Yeah.
Wow. So you stayed in physics all the way through your degree programs?
Mm-hmm.
Wow. And how did you end up finding your way into the fields of electrical engineering?
I didn't switch fields. What happened is that my research field has migrated in time, mostly from physics departments to mostly EE departments.
Got it.
So the first people working in the area tended to be in physics departments, and then as it got to be a more developed area, a lot of their graduates ended up in engineering departments because the area was closer to applications.
Got it.
So I'm generally in optics and photonics, and in optics and photonics you will find people from a variety of departments. So some people are EE, some people are applied physics or physics, some people are even materials science or chemistry, depending what they do. So if you come up with new materials for photonics, you might easily be a materials science person or a chemistry person. If you study purely how materials respond to light and what you can do in applications in optical communications, say, then you might be an EE. If you, some people are even in mechanical engineering. So
interesting.
At the conferences that I go to and in the professional societies that I belong to, there's a mix between all these different departments.
I think a lot of our audience is prospective students. They're high schoolers, and so we always try to formulate our conversation around that lens. And we tend to have high school students or parents of those students that are trying to figure out where they land on this spectrum of science and engineering. And from a high schooler's perspective, they see zero, from a lack of better term, engineering. How would you help them understand that bridge or is it important to even understand that they need to define themselves as a physicist or an engineer at this point?
I think the big distinction is in what type of jobs people take right after undergrad. So there are certain areas of engineering where it's very important to be qualified as that type of engineer. If you want to design bridges, you can't do a physics degree and then go out and get a job for Department of Transportation certifying that bridges are safe. You need to have a certain training that is a pre-professional training that would put you in a position to do that. If you're more interested in sort of future technologies, next generation technologies, being part of a research and development team eventually, then this distinction between scientist and engineer is a lot less important. So I think there's a range. If you're the type of person who wants to get a practical engineering job right out of undergrad, you absolutely need an engineering degree. If you're the type of person who might want to do a PhD eventually. At the PhD level, there's a lot more crossover between both different types of engineers and science and engineering.
If you can remember back to your high school days, what kind of student were you in high school?
It was interesting. I always really liked the theoretical fundamental stuff, and I always was curious about applications as well. And so I'm not sure that I really decided at that point. I mean, I liked physics, I liked the abstract stuff, but then I'd be curious, how is this used? How do you see this in everyday life?
Mm-hmm. You like the end-use applications? It was curious for you.
Yeah. I was, I didn't go into engineering as an undergrad. I went into physics, and I think at the time I thought engineering was mostly about things like those egg drop contests. And those stressed me out, actually.
Did they?
Yeah, I went to an egg drop contest of some kind. So I'm from Cleveland, and we have Case Western Reserve University in Cleveland, and they would have things like that where you go for the egg drop contest. I thought, you have to be good at the egg drop contest or you shouldn't be an engineer.
Interesting.
Mm-hmm.
So like those trebuchet contests
pressure.
And the egg drop, like all those different like little
I don't know,
games.
here are like 16 straws and 5 pieces of cardboard, and we're going to drop it off the second floor. And
what stressed
if your
you out
egg
about it?
drops, if your egg cracks, maybe you're not
You're not an engineer.
maybe this is not the right.
What stressed you out about it? Was it the competition of it?
I'm like, I don't know how to design an. I mean, really? Like, I've never designed an egg drop
thing vessel.
before, and now you're going to decide. I mean, are there principles? Like, are there design rules here? Can you give me any tips? There was nothing to go on.
Got it.
There was nothing to go on. I have found this actually both in physics and in engineering, that some professors have this really annoying habit of thinking you should have intuition about things that you have no intuition about because you've never seen them before. So this happened in freshman mechanics. I know our professor was talking about pulley problems.
Okay.
So he works it out on the board. He's like, but intuitively this makes sense, right? Like, obviously in this situation, you know that this weight has to go up and this weight has to go down and this weight... I'm like, really?
No, he knows that.
You know that.
He's projecting his knowledge.
I've never played with, I've never had a physical pulley of the type you just drew on the board in front of me for any reason ever in my last 18 years. So how would I know that?
We all have our pulley system set up in our bedrooms in high school that we use, of course, regularly.
Yeah. So I do think that's something that sometimes faculty lose sight of what's intuitive and non-intuitive just because...
What's common knowledge?
Yes.
What is there.
If you've known it for 20 years, it seems intuitive, but that doesn't mean that your students have ever seen anything like it before. So
That's true. Outside of this journey to science and eventually engineering, in high school, were you what were the things you liked to do? What type of student were you? Or did you like the books? Did you get engaged in other activities?
Let's see. So I did debate. That was fun. I won the Ohio State Lincoln Douglas debate competition. I was really fortunate. I was not the best debater in the state throughout the normal season, but I got really lucky. The finals round, I got lucky, and I got the negative case about 5 times in a row. Oh. And it so happens that I'm really good at the negative case and not as good at the positive case of Lincoln Douglas debating, or at the time. And I kept getting negative, and it was great. So I won states. It was
That's awesome.
Fun. And what else did I do? I was in some school plays, and I briefly ran cross country my freshman year, but only 1 year. And that's all I can think of at the moment. Probably did some other things.
Yeah, I'm sure. It's always funny because when you're in high school, you think like you're going to remember every moment of this. And we're reading applications right now, so the reason I'm asking is I'm just going through all these applications and trying to understand everybody, and it's always funny when you get out of it, all these things start like replacing your memories as new things that you do and new exploration, whether they be academic or professional or just friend groups. Your whole life changes as you move.
Oh, wait, here's a good one. I took Latin by mail.
By mail?
Yeah.
Correspondence course?
This was kind of before the internet, so when I was in high school, the internet existed, and people had dial-up modems at home, but there wasn't a lot of interesting stuff on the internet. So, it wasn't like today where anything you want to know, you look on the internet. So this was Latin by mail. So there was a teacher who lived in Illinois, and I had a book, and I would do exercises from the book and then mail them to her, and she'd grade them and mail them back.
Really?
Yeah.
What is this something that you wanted to do? Like you were so passionate about? Like, it feels
Yes,
like a lot
unbelievably enough, this is
Really?
something I wanted to do. We didn't have Latin in my school, and I was pretty jealous. I went to an all-girls school, and the all-boys school had Latin.
And so therefore,
And so I thought this was really a shame that we didn't have Latin too, so I did it by mail.
was this Ursuline?
No, Magnificat.
Okay.
Yes. I think they have it now.
Okay.
I think they've expanded the language programs quite a bit, and I think they now have all the languages that
Okay.
our local all-boys school has, but at the time we were behind a few languages.
Got it. Well, do you think it was an interest in Latin, or was it because the boys' school had it?
Well, it's a toss-up. I do really like languages. I've learned a bunch, not by mail, but at different times. And I really enjoy grammar, and
Oh, cool.
Latin was a good introduction to that. I really like, I really like understanding the structure of different languages and how when you learn new grammar rules, you can say more stuff. And
Yeah.
I always found that pretty fascinating.
Yeah.
So, you start out, you can say like, I eat, I walk, and then you get to past tense, and it's really exciting because now you can express this whole new class of stuff. I ate yesterday.
Past perfect is my favorite.
Yeah, that happened. I spent a summer in Japan after undergrad, and so this was happening in real time. Like the people around me didn't feel comfortable talking to me in English, and so I'd go into the lab every day. I was working in this lab, and I didn't know Japanese before I went. I started studying I had no idea I was going to be going to Japan. It just turned out that I did, and so I get there and I know very little. I'd started studying a few weeks earlier. So yeah, the first day I can say, hi, I'm Michelle. And then, like the second day I can say it's hot today. And then eventually I can say it's hot today and it was hot yesterday. And then over the course of the summer, the number of things I could communicate with people expanded, and it was really cool. And I was like, okay, this is fun. So yeah.
What languages do you have under your belt?
So it turns out that I don't speak anything particularly well. I just learned
Yeah, you skim.
a bunch of
Yeah,
languages.
sure, yeah.
First time. So I learned French in high school, and then I learned Spanish in grad school, and then I learned Japanese just by being in Japan for a while, and Latin by mail.
Latin by mail. Do you have a favorite?
No,
No.
not really.
That's cool. I love. Do you speak any other languages? I don't know if I know this.
I did French in high school. My parents, interestingly enough, they speak Bengali, which is like an Indian language, at home. That was not my first language, though. English was my first language. And when I was little, they would talk to me a little bit in Bengali, but not a lot because they wanted me to assimilate into my school or something. But now it's super frustrating because I wish I could speak it.
Right.
But so I can understand everything. I know what they're saying, but I can't speak it back because I never learned that grammar fundamental type stuff when I was a kid. So I can't hold a conversation. And now if I go back to India, people will speak to me, but I respond in English, and it's so embarrassing. So it's a little bit of a personal frustration for me. But French, honestly, I speak more than my mother tongue, I guess.
Yeah.
Yeah, which kind of sucks, but
Yeah, I think
it's my
that
language story.
it definitely happens. So, what year did you start here at USC?
2008.
2008. All right. So we're going on 11 years now.
This is my 11th year,
This
yeah.
is 11th year as well. And what initially, what were your thoughts about USC when you joined us, and what do you think about USC now? I mean, you've been at a number of different universities.
Yeah. So I wanted to come here because of the strength of engineering. Electrical engineering is a very strong department, and we have a lot of historical strength here in electrical engineering, but we also have really amazing hiring over the last 10 years, 11 years that I've been here. So the number of new hires in EE and across engineering as a whole has really made it an exciting place, in that we have a lot of people coming in with a lot of energy and different variety of research programs that are really increasing our research strength. So it's been a good time to be at USC, I think, for that reason.
Had you been to LA before?
No. LA is very confusing when you haven't been here before. I had been here for a conference at UCLA. I think that was possibly the only time.
Okay.
Yeah.
Okay. And what are your thoughts on LA? Now you've been here for over a decade.
LA is amazing. It has the best and worst of everything. So you spend all your time initially figuring out how to experience the best parts and avoid the worst parts. So they're just things you learn not to do, right? I mean, say, okay, so should I drive from USC to Santa Monica at 8 a.m.? No. You should just never do that, right? I mean, like, should you, try to drive from Malibu to Santa Monica on Saturday at 5:30 p.m.? No, you should just structure your life so that never happens.
Yeah.
So
you get to know the traffic flows pretty well.
Yeah, it's all about traffic. So
At least it's
for those
predictable,
not in LA, they don't know this, right? For us who live in LA, we know this. So the usual conversation is someone says, how far away is such and such? And you're like, 20 minutes to an hour. Depends on traffic.
Yeah, minutes. I think we're the only city that does that, right?
15 minutes to an hour and a half. Depends.
Right. Or when are you going? And then they'll give you a better sense of it.
Right. So yeah, I think just adjusting to the traffic and what you should not try to do in one day was the biggest hurdle initially.
That's a big one.
I know when I came here to visit, after getting the offer, but before living here, I knew people in different parts of the city. Mm-hmm. To be like, okay, I know someone. Apparently they live in Pasadena. I know someone else. Apparently they live in the Hollywood Hills. So we'll go meet the first person for brunch, and then meet the second person at 3 to go to the museum. And then after a while, you realize you should just not.
Geographically, it all makes sense, right?
That.
You see someone that lives in LA, you're like, oh, you live in LA. Great, cool. They live in Santa Monica. You live in Pasadena. That must be close. No, that's not close at all.
Right.
Those are each an individual day.
Yes. Yeah. So once you get over that, there's really amazing stuff here. There's everything. Everything that you might want to find in the world is probably in LA.
What part of LA did you end up sitting down or settling down?
I live very close to campus.
Oh, you? Okay.
So
you're right in the center of it all.
Yes.
Makes those trips equally or equidistant.
Right. All the trips are equidistant. Yeah. So that's what I always tell people. Like, if you want a Vietnamese restaurant, I'm sure there are probably at least 40.
Yeah.
So you can find one.
Yeah.
I was in Korea about a year ago, and I kept reading. I was in Seoul, and I was reading this guidebook about what to do in Seoul. They'd say, okay, there's this special ginseng chicken place. It specializes in ginseng chicken. It's different than... And I'd be like, yeah. I went to one of those last week in Koreatown, and we don't need to go again. They'd be like, okay, there's also this place that specializes in this Korean-style dumpling. I'm like, yeah. I went there with a friend 2 months ago. We have
it's on
one
Western.
Of those.
It's right there. Yeah, we're good to go.
Soft tofu place. Yeah, I've been. So it's any kind of food you want or outdoor activity, hiking, ocean-related sports, going to the beach, kayaking, fishing, like anything you would want to do, even skiing, right? We can get skiing.
Oh, yeah.
Anything you want to do is within...
We do take it for granted.
An hour.
Yeah.
You just need to make sure you don't go in traffic.
go around the traffic.
Yeah.
And when you've been here, you've done an incredible amount of research. And I think if I could summarize it in one word, it's nanophotonics. Is that a good justification? Can you tell us a little bit more about your research areas and what
Sure.
it does?
So I generally study how light interacts with materials that have very small patterns in them. So for reference, just one hair, if you take the diameter of your hair, that's about 100 microns. So if you go 1,000 times smaller than that, we study what happens when you make holes that size in materials and how that changes what they do to light. And the reason that's important is because we can use that information to impact different application areas. So in the early part of my time here, we spent a lot of time on nanostructured solar cells. The idea was that instead of using a totally flat, solid panel for a solar cell, we could actually make a solar cell with little tiny holes in it, and putting those holes in there played some tricks with the light. It got the light to go in and recirculate a lot. And by doing that, you could use less material, which in some cases could make the solar cell cheaper. In some cases would allow you to use a different fabrication process that might have advantages for cost in the long run. And so we studied different fundamental problems having to do with how exactly do you make these small holes in the material to make it trap and recirculate light better. And then we estimated what that would do to overall solar cell efficiency, and then we tried to relate that to relate that to what the ultimate cost savings might be in terms of processes. So that was one example of a application area. My group's also done a lot of work on optical trapping. So optical tweezers won the Nobel Prize this year. Nothing to do with me or my work in particular, but my work has been inspired by that whole area. Okay, it has something to do with me. I just mean it wasn't my work that won the Nobel Prize, but my group has benefited from that tradition. So the idea of optical tweezers is that you can actually, if you take a laser and you focus the laser on a small object, that light can actually grab and manipulate the small object.
Wow.
So this is sort of a fun fact. We don't notice this usually, that light can exert a force on objects. So the example I like to use is that if you're sitting under a light in the room right now, you don't feel it pushing on you. But there is a tiny push. You don't feel it because that light is not strong enough for you to feel it, and you're very heavy, so you don't go anywhere. But when you go down to very small objects like nanoparticles or blood cells or bacteria, and if they're floating around in solution and you take a laser and focus the light on them, it's strong enough to actually grab things, move them around, in some cases stretch them. And so there are different techniques where you can manipulate objects using these forces of light. And so my group's also worked in that area. We study how to get hundreds of really small particles to line up in an ordered way and form a pattern using light. And to be able to bring those particles in to build a material from the ground up by putting particles where we want. We can either let them go again by turning the light off, or we can lock them in place using some polymerization methods where we keep them there permanently. So we're thinking of this as it's an alternative way of building up structured materials from the bottom. And then we will be looking at different applications of that. So in some projects that we did with optical trapping, we were stretching on cell membranes to measure how stretchy they were. That was work that we did with Noah Malmstadt's group. And in other projects, we're seeing how we could maybe bring together lots of small particles to run tests on them, or as a way of catching them and doing biological tests, or as just a way of making materials that we could then use for other applications, like our solar cell application or other work that we're doing.
Right. So does this mean that, with a certain intensity or I don't know, size of the force of the light, meaning let's say you got a giant laser, then if you get it strong enough and big enough, that starts to move bigger objects that aren't nanoparticles?
So in fact, a really fun example of that is solar sails. So the solar sail is something you learn about in physics when you first learn about this general phenomenon called radiation pressure. So the idea that if light bounces off of something, it actually gives it a push is called radiation pressure.
Okay.
And one example of this is solar sails. So if you want to propel something in outer space, because you're in a vacuum and there's no air resistance, you can actually use light to either the sun or a laser. You can use light to push things around. And there have been different missions that have tried to do this. And there is actually one now, which there's a project called Breakthrough Starshot, which is funded by a billionaire.
They all are, right?
And the goal of that project is to try to send a camera to Alpha Centauri. And the proposed mechanism is to use a really strong laser on the ground and aim it at one of these sails up in space. And the laser would push on the sail and propel it, get it up to speed, and then it would drift off to Alpha Centauri.
See, I'd always assumed solar sails were just a way of getting solar panels out to absorb energy, and they were lighter. That's what I always thought. I never knew that it was always just to actually catch the laser like a wind.
Yeah, like a wind.
Huh.
Yeah. So, these are both examples of the forces of light on objects. You can either just push on things, or in certain circumstances, you can use a focused laser to grab things and move them around. Or in slightly different devices, which we design, you can stretch things. Or in other devices we've come up with, you can grab 100 things and space them in a particular way close to each other in a pattern. So these are all different examples of what you can do by manipulating the light and the object.
I'm totally imagining like cartoons and sci-fi here, where there's like an evil person with a laser gun that does something, right? That's my like.
Star Wars, like.
The lightsaber.
Yeah.
I didn't even go that. That's an easier pull.
Yeah, that's literally what I thought of.
I was imagining like this gun that takes down buildings, like a laser.
So it's interesting what the laser does to the object. Sometimes it moves it around, and sometimes it heats it up or burns it. So we also use, not we, but humans.
Yeah. The royal we.
Yeah, the royal we. Humans also use lasers for micromachining and welding. Uh-huh. So under certain circumstances, you aim a laser at a thing and it burns it up.
Right.
LASIK,
Yeah.
Under certain circumstances, you aim a laser at your eye and it cuts or ablates the tissue. Mm-hmm. So understanding when you're damaging a material, when you're burning it, when you're pushing it or moving it, when you're heating it up, all of those things fall within this general optics and photonics field.
Cool.
And all of those have applications. So we have another project where we use lasers to heat things up rather than push on them and create small bubbles where we want them. So you can make tiny bubbles in a desired location and use that to push fluids around and manipulate them.
Oh, cool. So out of all of these possible end-use applications of where you could see it possibly going, what do you think is the closest to us or the most likely? Is that smaller solar panels or?
Well, okay. So in general, the nanostructured solar cell area, that has some industrial effort now. So I have a student who, after he finished his PhD, he went to a startup that was working on that.
Cool.
I have to check back in to see how they're doing, but I think those ideas are being used. And of course, we're not the only ones working on that. So all these things that I'm mentioning, the fields that we've worked in my group, they're tied into larger academic fields that a number of researchers are participating in. So there have been different approaches and different methods to study this general idea of the nanostructured solar cells. And I think that will probably find its way into industry in one form or the other. The optical trapping, the main application of that area so far has actually been for research rather than for
commercial use.
Commercial, but I have a student who graduated from my group with a PhD who's now at a different startup that is trying to commercialize it. He couldn't tell me that much about what the application is, so I'm not sure I can say it on air, but they do have an intended commercial use, and we'll see if they're successful at that. And so these are, so we'll see how these startups do and how it does in industry.
In your work, specifically, I think is related to the photovoltaics. I can't say that word sometimes. Photovoltaics. You on your research website, you talk about using the USC supercomputer for this work.
Yes.
And so, can you tell us a little bit more about? I think, first of all, how does someone understand what a supercomputer does and how that was necessary to do the work?
Sure. Okay. So
that's just the easy answer, right?
Right. So we do a lot of design work in my group. I mentioned the case of making really small holes in solar cells. Mm-hmm. So the question is, how big should the holes be? Where should you put them? Should you put them in a regular pattern or a random pattern? What should you choose to get the best performance? So to answer that, we have to solve or simulate the equations that govern the interaction of light with the material, which are Maxwell's equations of electromagnetism. And so you need some way of solving those. And for these complex structures, like materials with lots of little holes in them, this isn't something you can do on paper. You need to do it numerically on a computer. You can use your desktop or your laptop, but it'll just take too long, especially when we're trying to optimize structures. So we're trying to find the best design. You have to run many cases and see which one does the best. And so for that, having as much computational power as possible is really useful, and that's where we use HPCC. So HPCC, the supercomputer, is really just lots of computers put together. They stack them up in racks, and what I mean by put together is those individual computers can communicate data with one another quickly. And so when you take a large problem, you can split the problem in pieces, give each computer a piece, and then they'll communicate back and forth as needed. And by doing this, you can run much larger problems, and you can also run more cases. So you can test more possible cases to find the best one. So a problem that might take, instead of letting your desktop computer spend 4 weeks to do something, you can get this network of computers working together to do it in a day.
What's that? So a typical desktop versus the supercomputer, what are we talking about? The order of magnitude?
HPCC is updating all the time, and I should look at the website to know the exact number, but they have thousands of nodes. Wow. So there are thousands of computers, so to speak, and then they'll use multi-core computers. So each computer is, faster at, stronger, faster, better than your laptop anyway, probably. And so they have many computers connected together, and then the connections are higher speed. So they connect them with there's a special type of cable that is faster than Ethernet.
Oh, really?
That lets the computers share information faster. And you do need that because if you split up a problem between computers, there is certain info that you need to pass back and forth.
Right.
And if you can do that quickly, the overall computation goes faster.
Got it.
So, we're really fortunate here in that there's a whole center that just takes care of this entire computing infrastructure and makes it freely available for faculty to use for research.
Yeah.
And they make it really easy for us. We just submit this brief renewal each year where we describe the research project, and then they give us free computing.
That's great.
So, yes, that's great that we have that here.
Very cool. Now, one of your other projects I think you're currently working on is you have a self-described term as thermal homeostasis. Can you describe?
Yeah. So
what that's
lately,
about?
I've been very interested in thermal emission. So we can't see it with our eyes right now, but all the hot objects in this room are emitting infrared light. If you get a thermal camera, so there's a cheap $200 camera you can buy now that goes into your iPhone, and you can look at things. And instead of showing you the color that we usually see, it shows you which things are warm. So people look warm. People are warmer than the wall.
Right.
Okay, so what that's doing is it's measuring how much infrared radiation is coming off that object. And the more infrared radiation you see, the hotter the object is.
Right. I can tell you my only reason I'm aware of this is because I watch ghost hunting shows. And
Yeah.
they use thermal
Ghosts.
cameras.
You can hunt, I guess deer hunters, wildlife hunters use them to find deer.
Far more practical. But
Yeah. And AC technicians. So you might see, if you're looking for leaks from your house.
That's cool.
At any rate, the idea that we've been looking at is the idea that we want to try to design a material that regulates its own temperature, kind of like a human, but in a different way. So we're warm-blooded, so we're regulating our body temperature, and we have certain mechanisms for doing that. We can sweat. We wanted to design an artificial material that could regulate its own temperature, but not by making it sweat. The concept is that we're trying to design a skin or a nanostructured material that would, if it gets too hot, it would radiate as much as possible to dump the heat, whereas if it gets too cold, it would try to not radiate at all to keep the heat inside.
Got it.
And so we're looking at different designs for materials that might do that and now starting to make them and test them and see if they behave the way we're expecting to help maintain temperature at some set point. Yeah,
Very
and
cool.
that's work we're collaborating with a few different labs. We're working with Naval Research Lab that makes a special material that's useful in this project, and then also with some basic researchers at Northrop Grumman.
Is the purpose, like end-use application of this more for like energy conservation?
Could be. The initial application that we were thinking of was thermal control in space for satellites. So when you're in space on a satellite, the only way that you can cool is by radiating. When you're on the ground, you might have wind blowing over your surface. Well, even as a person, if you have wind blowing over you, that helps. You lose heat, you get colder.
Right.
Since there's no wind in space, and you're also in a vacuum, so you're not in touch with anything else that you could lose heat to, then radiation becomes more important. And so we were looking at this as a way of helping regulate satellite temperatures.
Huh. Interesting. Very cool. And you also had another fascinating project where you were working with the School of Pharmacy. That's a different project?
Yeah, that's an example of using lasers to heat things up selectively. So we are making something like a modified microscope slide where when you shine light at it, certain parts would heat up. And we wanted to test the ability to heat up different areas in fluids with something that responded to heat. And Andrew McKay, who's in pharmacy, he studies temperature-sensitive peptide chains. So there are these temperature-sensitive molecules. He uses them for drug delivery. But what's nice for us is that at a certain temperature, they clump up. And you can see that happening. And so we're putting those things that clump up on our special slides and trying to trigger that process and demonstrate that we can heat selectively or in different areas of the chip.
Huh. Very cool.
Really cool.
That's awesome.
Yeah.
And you do you see anything in your near future of things that might be changing for your research or new projects you might be taking on? Not that you're not doing enough now. I don't want to make it seem like...
Yeah, so we're working on... Lately, we have been working on lots of projects that involve both light and heat.
Okay.
I would say it would be a theme. So I started out really looking at optical effects, and in a lot of cases, things would heat up by mistake. And so over time, I started looking at that more on purpose, rather than looking at heating as this annoying consequence of using lasers. I've been trying to really look at problems where we're deliberately heating things or deliberately controlling temperatures or deliberately controlling how they radiate.
Okay.
So we've also recently been working on something called, so we have a paper we just are publishing now. It's coming out in press, which is about thermal memory, which is really far out. You asked about applications. This one's really far out. The idea is that far into the future, in certain extreme environments, our computers could break down. Let's say you want to go to Mars. Your computer might not work on Mars. At high temperatures, your computers stop working. So there is some very scientific interest fundamentally on other ways of doing memory and logic that wouldn't be the way your computer's made. And we've been looking at something called thermal memory, which is trying to store information in how hot an object is rather than what electronic state it's in.
Interesting.
So this is a field. It's right now it's really more of a science field than an engineering field because the devices aren't super practical.
Just super theoretical, just out there.
But any electronic device you could think of, like logic gate, where you're manipulating electronic states, you can, in principle, look for ways to do that with temperature. And so this is something we've started looking into recently. We think that there might be a way to make those devices more practical using hybrid optical thermal devices than some of the previous proposals that people have put out using sort of thermal devices alone. And so we've started looking at some of those. So we have a memory paper that we are publishing the next few weeks, which is about trying to store a bit of information in the internal temperature of a device. And then we're also looking at extensions, like how do you make gates or how do you make logic.
What happens as the device changes temperatures?
So
if you're storing
the way this works is what we're doing is the general idea of a thermal memory is that you need to have something that can stably sit at two different temperatures, and then you need a way of pushing it between them. So then depending which temperature it's sitting at, that's either 0 or 1. So let's say you're in the cold state, that's 0, in the hot state, it's 1. But you have to design the system so that you definitely end up in one of those two and not somewhere randomly. So there are certain systems that satisfy these requirements, and you can design them to do that. In our case, we're using this system where we use a laser to control whether you're in the cold state or the hot state, and then also to read out which one you're in. And theoretically, the advantage is that this device can operate in a really high temperature, much higher than your computer could. The disadvantage is that right now we can only make one bit and store one bit of information. And so certainly it's not going to be a laptop tomorrow. But,
right.
But I've been interested in this, what else you can do within this paradigm of what other computation elements you can build up.
Is there, to me, all of a sudden, I don't know anything about this, but is there some sort of link between then the radiation and the ability to then to energize itself or to like keep that type of energy going?
Yeah, so in this memory case, we have to use a laser, and the laser has to stay on. We change how intense it is to switch from 0 to 1, but if we turn the laser off completely, you would lose all your information. So, yes, we have a memory that requires a laser.
Got it.
Right now. There are other approaches you can use where you can turn the laser off by using special materials that can sit. There are some other approaches that wouldn't require your laser to be on all the time, and those are also interesting.
Cool. This is great. Are you teaching anything right now, or just focusing on research?
Yes. So I teach every semester in the spring. Last year and this year, I teach freshmen. We have a new class that just started last year. It's a joint effort between physics and electrical engineering to teach freshman engineers physics. So it's a bit of a different format. The physics department professor teaches the lectures, and then I teach the discussion. So in the discussion section, we take the theory from the lecture and we relate it to example problems, and I choose the example problems so that they're more applied than the usual physics class. So we make an effort to pick things that you hopefully have seen in everyday life or that you will see in your future engineering work. So, for example, we just This is the first week, last week.
Yeah.
So, we were talking about acceleration and projectiles, and we looked at how many G's you experience when your car accelerates on the highway using real numbers for 0 to 60 mile per hour acceleration times. So we're covering standard topics that you do in a freshman mechanics class, but with an eye to practical examples.
Right. Is this a special section of one of the physics courses, or is it a whole new number?
It's a new number. It's 171, and the goal is that there will be a 171-2-3 sequence, which will be an option for freshman engineers. They can take in place of the
151,
traditional 151-2-3 sequence.
Right.
So far we have students from AME and EE taking it, and this is the second year around.
That's great. And have you been enjoying that?
Mm-hmm.
Yeah.
It's fun. Examples are fun.
Yeah. I think it's an extension of the model that we started a while back with calculus, where we started having some of our electrical engineering faculty teach sections of calculus for engineers here. Well, they were just different sections, and then we had some different versions of them as we went along, and so hopefully this makes the stronger connection for an engineering underclassman to connect some of the physics theories or the mathematics theories to where they're going with this, and hopefully help with that pipeline as we move along. So that's great. We've covered a lot of topics. Is there anything that we haven't covered that you wanted to talk about?
So since there are potential undergrads who listen, and perhaps potential grad students, who knows?
Who knows? We got a lot of listeners, yeah.
So I would say for potential students, I really want to highlight the opportunity that you get here to get involved in their research groups. One of the things I really enjoy most is working directly with my students in the lab on research projects. We mostly have PhD students, but we've had a number of undergrads who've been able to do projects with us. Last year we had 2 seniors who did senior theses and then went on to grad school afterwards. We've had other undergrad interns through the years. We usually have 1 or 2 a year. And that's pretty typical of a lot of the labs here. So a lot of the labs here have undergrad involvement. And that's one of the real advantages you get by coming to a research university, is seeing what research is like, being able to participate, and taking part in projects. So I encourage students who come to really check those opportunities out. I think USC has done a lot to make it easier for students to get involved in research. We have different programs where you can be paid to do research, where you can get a fellowship to be sponsored for the summer. So I've had a lot of students do that, and to try to build awareness. And it's really something to take advantage of. If you if you go to a research university like USC, that's just a big resource that you have that you don't get if you're going to a more teaching focused school.
Right. That's great. Well, thank you so much. I really appreciate you coming in. Great job. Awesome.
And that's just about it for this week's episode. Thanks so much for tuning in. We release new episodes every Monday, so follow us on SoundCloud, Apple Podcasts, Stitcher, wherever you get your podcasts. We are on Spotify now, so you can shoot us a follow over there too. But we'll catch you next week. Peace out and fight on.